In this chapter, we're going to be discussing how to estimate the value of a parameter. Let's read through the following paragraphs. In this chapter, we're going to be talking about inferential statistics, the process of generalizing information obtained from a sample to a population. We will talk about estimation, using sample data to estimate the value of the unknown parameter in the population, such as the population mean, population proportion, or even population standard deviation. Let's say that we would like to estimate the proportion of adults who prefer Christmas over birthdays. We cannot possibly survey every single adult American in order to find out the true value. So what we do is we use a sample of adult Americans in order to estimate the proportion who prefer Christmas. A point estimate is the value of the statistic, such as the sample proportion that estimates the value of the parameter, such as population proportion P. For example, let's say we surveyed 100 adult Americans and we found that 76% preferred Christmas over birthdays. So that means P hat is 0.76. But again, this is just an estimate for the population proportion P. One thing of note is that a sample proportion will vary from sample to sample. So what we can do is construct an interval for a population parameter based on a guess for the value along with the level of confidence. This is what we call a confidence interval. A confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. Back to the example above, P may not be exactly 0.76, but we can say P is likely between something lower like 0.66 to something higher like 0.86. But how confident are you of saying this? The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted by 1 minus alpha, where alpha is the amount you're willing to risk in making a mistake. If you're willing to risk 5% error, that P is not in your interval, then your level of confidence will be 1 minus 0.05 or 95% confident. Confidence intervals for the population proportion are of the form, take your point estimate and then we add and subtract what the margin of error is as the tolerance. And this will give us our interval. Let's draw a picture of what we're depicting so far. So let's say for the previous example, we get a point estimate, which we'll call for this example P hat, and that will be our point estimate. Again, this point estimate is coming from a sample. A sample is something realistically we can go out and obtain. This is what we call our best guess. Then we say, okay, well, the population proportion is probably going to be close to whatever this value is, but it might not be exactly. It'll probably be somewhere within a tolerance or a margin of error of that sample proportion. So we'll have a lower limit and we'll have an upper limit. And our population proportion will be between those two numbers. How do we find what those two numbers are? Well, we find what is called the margin of error. And when you find the margin of error, we're going to subtract and add it to our point estimate, and then that will give us our lower and our upper limit, or our range, of which we decided that our parameter is probably inside that range. For example, a 95% confidence implies that if 100 different confidence intervals are constructed, each based on a different sample from a sample population, then we will expect 95 of the intervals to include the parameter and 5 will not. So what will happen if we want a higher level of confidence? Let's say 99% confident. Will our interval become wider or more narrow? So what I like to do is think of this as a target practice. Let's say that you're playing darts. Let's pretend you're in the classroom, right? If you were in a classroom, up at the front of the classroom, you would have a whiteboard or your chalkboard. On the chalkboard, I would draw a target with a bullseye, right? So let's picture this target on the whiteboard. Let's say you're 95% confident that you can hit the target. So I'm 95% confident I can hit anywhere inside this yellow circle. So you stand at the back of the room and you say, okay, I'm 95% confident with my dart, I can hit that yellow circle on the board. I'm 5% not confident, meaning 5% risk of making an error, that I won't hit that yellow circle. Maybe I'll hit the board or maybe even outside the board. How confident then would you be to hit a larger area like the whole board? So let's say, how confident are you that you can hit anywhere in this white space? It doesn't have to be the target. I'm giving you this larger interval. Would your confidence increase or decrease? Well, of course, you would be more confident because when you extend the area and make the area larger, I become more confident that I could hit a larger area. So then I become something like 99% confident. So basically, as your interval size or the size of your area increases, your confidence will also increase. So the same would be true for the other direction. If I said, what would be your confidence that you could hit this tiny little bullseye in the middle, right in here? It would be very unlikely, right? Because it's a small little interval, it's a small range. So you're not going to be very confident. Maybe you're only going to be 90% confident or something even less. So again, as my interval then gets smaller, my confidence also gets smaller. So they both go in the same direction. As interval increases, your confidence increases. As your confidence gets lower, your interval gets smaller. So they are directly proportional to each other. Okay, so keeping on with this notion, let's dive in just a little bit deeper. In this particular page, it says we're talking about common confidence levels. 90, 95, and 99 are the three most confident levels that we discuss in this book. Can we be 100% confident ever? And the answer is going to be no. We can never ever be 100% confident of anything. The closest we can get is 99 or 99.9%, but there's always a risk of being wrong. A 95% confidence interval is going to look like this normal distribution curve, which we talked about back in previous chapters. This normal distribution curve, we know that 95% of our data lies within 2 standard deviations of the mean. So we already know that our confidence interval is going to be the shaded area with this 95% in the middle, which means we're willing to risk the possibility of being 5% wrong. The 5% wrong would be in the tails over here. This area on the sides, these would be our two tails of our willing to make an error. If I'm willing to make a 5% error, there's going to be 2.5% on this tail and 2.5% on this tail, meaning 2.5% of the time I'll be wrong, I'll be too small. 2.5% of the time I'll be wrong, I'll guess too big. So these areas and these tails are going to be alpha divided by 2 because I had to split this risk into 2 separate tails, and they are both 2.5% of width of probability. Also associated with that, I'm going to have z-scores, okay? These z-scores right down here are going to be a z at this particular confidence, which is alpha over 2. And if I go to my z table, you'll be able to find that z value. So if I go to in your book, it's going to be table 5, which is your standard normal distribution table. And if I look up a probability of 0.025, I'll find the z-score attached to that. So if I look up a z-score of 0.025, it's right here, 0.025, which has a z-score of negative 1.96. Negative 1.96. And since it's equidistant from the mean, that means this z-score is going to be positive 1.96. Now, if you look at the bottom of your table where we were just at, you'll also see those values down at the bottom. So for a 95% confidence interval, you see that the critical z values are 1.96. So they already extrapolated it from the table and put it into this nice little grid for you down at the bottom, so you don't have to search for it each time. They are listed down here. Let's look at the next one. Let's look at 90%. So let's make a smaller interval, okay? So let's say this one is going to be a little bit smaller. So now we're only talking about 90% on the inside. So 90% confidence. That means my risk of error is going to be 10%. So these tails are going to be 5% apiece. So this alpha over 2 and this alpha over 2 are going to be 0.05 in probability each. Their particular z-scores, again, if I look up a probability of 0.05 in the table, I look up a probability of 0.05, I get a z-score of somewhere in between these two values, which is going to be negative 1.6 for halfway to 5. Negative 1.64 halfway to 5. Negative 1.6, it's actually 4.5. And again, those values were listed at the bottom also. Look, for 90% confidence, we have a critical z-score of 1.645. And obviously that's a negative and a positive. You're going to have a negative on the left side and a positive on the right side. All right, let's do one more. Let's look at 99% confident. Clearly, we're going to have really small tails. So this is going to be a much wider range. Okay, so if we're looking at 99% confident, we only have tiny little tails out here because our alpha is going to be 0.01. So these little tails are going to be half of that, or 0.005. So those z-scores are going to be pushed even farther out. They're going to be larger than 1.6, larger than 1.9. They're probably going to be closer to 2 point something because they're even farther away from the mean. So again, if I go to my table and I look up this probability of 0.005, we're going to get a value of halfway in between these two values right here. So our z-score will be negative 2.575. And again, those are written down here anyways. So for a 99% confidence, you're going to have a critical z value of 2.575, either negative or positive. So we got our z-scores. Let me write those in. So these are going to be the three most common that you're going to incur. In the table, they also do a 98% confident. Clearly, you could have done one of those as well. But those are going to give us our lower and our upper bounds. Now these z values, which are z of alpha over 2, are going to be used in the following formulas down here. These are the formulas in calculating what those upper bounds are going to be. The first thing we're going to need to do is we're going to need to decide whether we have a graph that is approximately normal. So for a simple random sample of size n, the sampling distribution of p hat, which is our sample proportion, is going to be approximately normal as long as n times p times 1 minus p is greater than or equal to 10. Now, we did discuss that back in chapter 8, so we always have to make sure that we have an approximate normal curve before we can get started. Also, you're going to need to determine what your mean and your standard deviation is, because that's what's going to tell us what the curve looks like. You need to know where the middle of the curve or your mean is, plus you need to know how widespread your data is by finding your standard deviation. So all of these first formulas tell you how to construct your curve. Is it normal? Where's the center? And what's the spread look like? Also, one last thing we got to determine is make sure that your trials are independent from each other. In other words, when sampling from a large finite population, make sure that the sample size is no more than 5% of the population, which again, this is we've talked about that in previous sections. So this is how you find the upper and the lower bounds. When doing this by hand, if you suppose that you're taking your data from a sample of size n, and the data and the result is of a randomized experiment, a confidence interval, 1 minus alpha. So if alpha is 5%, you're willing to make an error, we're looking for a 95% confidence interval, is given by the following quantities. So p hat is your point estimate. Z of alpha over 2, that's your critical value. Again, p hat is your point estimate, n is the size of your sample, and everything in this circle is what we call your margin of error. Or for short, MOE. Okay, so there's always going to be two parts to this. You're going to have your lower bound, which is going to be your point estimate, and we're going to subtract the margin of error to find the left side, and then to find the right side or the upper bound, we'll take your point estimate and we'll add that same margin of error. So the critical, what are the values of the above circles? I already discussed those. These values are called your point estimate and your margin of error. So I think we're ready to go through an example. In this example, we have a survey of 3,611 adult Americans aged 18 and older, and we're going to conduct this back in July of 2010 by a company called Smart Revenue. And they found that 542 of the sample size used their smartphone to make a purchase. Now, clearly this survey is quite old, because I do believe the proportion has since went up. I do believe a lot more than 500 of the 3,000 would be making purchases on their smartphones nowadays. But we'll use this old data for this example. The first thing it tells us to do is to obtain what's called a point estimate for the population proportion. Clearly, we don't know what the population proportion is, but a point estimate would find the proportion of my sample. The proportion of my sample is what the percentage is of the people that use their smartphones to make purchases out of the total. So we would just divide x divided by n. In this case, it's going to be 0.150, or 15%. So this is going to be my point estimate, and that's what we're going to use to infer what the population proportion probably is. In other words, the question is, what proportion of all adult Americans use their phones to make a purchase? Well, it's probably close to 15%. It's probably not exactly 15%, but probably somewhere around here. So we have to create that range of which we think the population proportion is in between. So what we got to find now is the margin of error that we have to subtract and add to that number. But first we have to make sure that we've met all the requirements. We have to first decide, is the distribution normal? To make sure that the distribution is normal, we have to verify that p n times p hat times 1 minus p hat is greater than or equal to 10. So we have to first verify that that is true. Well, let's see. N in this example is 3,611 times p hat, which is 0.150, times 1 minus p hat, and clearly that is greater than or equal to 10. So I have definitely proved that the graph is normal. We also need to find the mean and the standard deviation. So now that we know that it's normal, let's find the center and the spread. The center of this graph is going to be located at the center of your p-hats. In this case, we'll assume that that's getting closer and closer to p. So we'll assume that the center will be 0.150. That's going to be our estimate. Our standard deviation is going to be the square root of p times 1 minus p over n. Well, we don't have p, so we'll use p hat for this example. So we're going to use 0.15 times 1 minus 0.15 over n. And when I put that into my calculator, I'm going to get 0.0059. Okay, there's one more thing I need to do to make sure the requirements have been met. Not only do we need to know that's normal, but last thing we also need to figure out is we need to make sure that our sample size is less than 5% of the total population. Well, clearly, the total population of all adult Americans is in the millions of people. So I can assume that 3,000 Americans is certainly less than 5% of all adult Americans in the country. So that has been satisfied. So my sample is definitely independent. So let's go ahead and construct a 90% confidence interval for this particular example. So using the formula from the previous page, we know that our upper and our lower bounds are going to be found by the following formula. P hat plus or minus z of alpha over 2 times square root of p hat times 1 minus p hat over n. So that's going to be our upper bound will be with the plus and our lower bound will be with the subtraction sign. So when I plug this in, our p hat we found up here, which was 0.15, that is our point estimate. Now we have to find our margin of error. Remember, our margin of error is everything in this yellow box. This is our margin of error. So we have to add and subtract that margin of error to our point estimate. So we're going to add and subtract z of alpha over 2. Well, we just got done finding all of those on the previous page. Remember, we're looking for a confidence interval of 90%, right? Our confidence interval of 90% yields a z-score of 1.645. These are the numbers that we're looking for. Also, don't forget that those numbers were also found in your table 5. So in your table 5, those critical z-values are found at the bottom where confidence intervals for 90% is 1.645. So you don't have to memorize those. So that's going to be my z-score, 1.645, times the square root of p 1 minus p over n. Well, we already found all of that up here. All of that information was 0.0059. So when I put all of this into my calculator, I get an approximation of 0.150 plus or minus 0.010. That's what all of this comes out to be. Now remember, this is my point estimate. This is my margin of error. So I get two bounds. I get a lower bound and I get an upper bound. So I'm going to write this in interval notation. When I subtract, the lower bound is going to be 0.140. When I add, the upper bound will be 0.160. So this is my interval notation, lower and upper bound. So a sentence that I would say, because it does tell me to interpret, I would say that we are, how confident are we? Oh, we are 90% confident. That the population proportion is between 14% to 16%. So that's what we're trying to find out. Remember, our sample had a proportion of 15%. 15% of our sample used their smartphones to make purchases. So we want to extend that to the population of the total country. So instead of saying 15% of everybody in the country uses their phone for purchases, we say we are 90% confident that it's somewhere between 14 to 16%. That's still a pretty narrow range. That's really targeted pretty closely. And the reason why we were able to narrow that range so small is because we had a fairly large sample size. Now, as you've noticed, as the sample size starts to decrease, let's say this was only 100 people, okay, that's obviously going to make a change in our standard deviation because you're dividing by a smaller number, right? So that's going to make my interval, that's going to make your margin of error actually a bigger number. So that makes then your range become wider. So as your sample size gets smaller, you have to have a larger range because you don't have enough evidence to say that your sample is definitely inferring the correct information. So the larger the sample, the smaller the range can be. So let's go ahead and do this one more time, but this time let's use a 95% confidence interval. The only thing that's going to change in this whole sentence is our z. Our p-hat's not going to change and our standard deviation's not going to change. The only thing that's going to change is your critical value. This z is going to change to the z that is associated with the 95%. And back, according to my table 5, using 95%, that has a critical z value of 1.96. So we're just going to redo this whole thing, and instead of this number, we're going to put 1.96. So why don't you pause the video here, and I'll go through it, and you go through it, and let's see if we get back to the same information. Okay, did you get what I got? So for a 95% confidence interval, again, you're going to expect your margin of error to get wider, right? Because as you become more and more confident, you need to widen the range that you're going to be in there. Because you're guaranteeing, you're becoming more confident, you're guaranteeing more often that your population parameter will be in this range. So you have to widen your range to make sure that it's there. So you'll notice that your margin of error, which is the second underlined number here, got larger. So the confidence interval then became 0.138 to 0.162. Or in other words, we are 95% confident that the true population proportion is between 13.8% to 16.2%. So again, you see how these numbers here got wider from the original numbers up here. So you can already assume what's going to happen in part E. If we were to construct a 99% confidence interval, we want to become even more confident, which means that this margin of error is going to become even wider. So the margin of error will become bigger, thus creating a wider interval. And I've already done this one for us, so let's go ahead and pull it up. You can see that it did in fact become wider because my margin of error got larger. So we are 99% confident that the true population proportion is between 13.5% to 16.5%. So the conclusion that we can draw from those above results, which we already knew, is as the confidence level increases, your interval has to get wider. Okay, so let's move on to a different scenario. Let's say, for example, that you want to make a certain conclusion. Let's work backwards. So I want to make this conclusion that I want to be 95% confident. So my question is, how many would I need to sample in order to obtain that information? And that's what this one is saying right here. How can we calculate the sample size that would be needed in order to estimate a population proportion if you know what that specific margin of error needs to be? And that's what most companies actually would do. They would work backwards. They know the statement they need to make in order to attract, the demand for their product. They know that they need to say 95% confident, or they know they need to say 99% confident, because that's the number that will attract their buyers. In order to be able to state that, they need to know how many they need to go out and survey in order to be able to make that statement. So they work backwards to figure out how many they would need to ask the particular question in their poll. In order to do that, we need to obtain the sample size n. Okay? But there's two different equations. One depends on whether you have previous information, and one is if you do not. In this first example, the sample size required to make a confidence interval is given by this, and that's if you have a prior p-hat, which means you've done prior estimates and you have an estimate of around what p-hat was the last time you did the example, but you're just trying to redo it again. So that's only if you have a prior estimate of a p-hat. Now, if you have no idea and you've never done a survey before, we have to use this n down here, which assumes you don't know any prior estimates. And this is going to give us a wider range because we have less information, right? So if you have prior knowledge, your n will not be as large that you'll need because you have previous information. But if you have no prior knowledge, this formula is going to generate an n that is larger because it assumes you have no prior information or no evidence. So also note in the bottom, it says when rounding, always round up. Okay, so if we're talking about how many people do we need in order to make a statement, we're always going to round up. We're always going to be conservative. We want to make sure we absolutely have enough people in our sample. Never round down, because then that might not be enough people in your sample. So let's do a quick example. Okay, suppose that a researcher wants to estimate the proportion of households that have internet access. What sample size should be obtained if she wishes the estimate to be within 0.03 with a 99% confidence? So she wants to be really confident with this small tolerance. So for the first example, let's say she has a previous estimate from 2009, and that prior estimate was 0.635. So that's my prior point estimate. So that's my prior p-hat. Okay, so using the formulas that I have up here, this formula is what I'm going to use because I do have this prior information. So my n is going to be p-hat times 1 minus p-hat times z of alpha over 2 over your margin of error squared. Okay, so let's find all of this information that we need. We already know p-hat. It was given to us in the problem. The prior information told me that p-hat was 0.635. Now, of course, that number might be different today, but it's a good starting point. Then we multiply that by z of alpha over 2. Again, we find that from table 5. You need to know your confidence level. If you are 99% confident, we're going to go to table 5, look up a 99% confident level, and we're going to find that our critical value is 2.575. We're going to divide that by the margin of error. The margin of error, I want to be within 0.03 or 3%. So then we put all of that into our calculator. And we're going to get 0.635, 1 minus 0.635 times 2.575 divided by 0.03 squared. And we're going to get an n. We always round up regardless of the digit. This one actually does tell us to round up, but even if this was a 1 in this position, we would always round this whole number up to the next whole person. So 1,708 people. It would be needed to be surveyed. So let's do it again for the next one, but this time we don't have a prior estimate. When we don't have a prior estimate, we're going to use the second formula where we have no prior knowledge. And that formula is n equals 0.25 times z of alpha over 2 divided by e squared. So notice it gets rid of all of this information in front where the p-hats were needed, and it combines those two pieces of information, just assumes it to be 0.25. But all of this information is the same as what we had up here. So 0.25 times 2.575 over 0.03 squared. And when I put that into my calculator, I get, of course, we're going to need a larger n because we have no prior estimate. So we're going to need about another 140 people additional. So 1,842 people would be needed for that particular example. Okay, let's do one activity. And this is going to use some prior information that we used back in the Chapter 8 notes. Okay, back in Chapter 8, we opened up a bag of M&Ms and we estimated the color distribution inside that bag, right? And we were looking at the proportion of blue M&Ms in the bag. So if you remember back from Chapter 8, if I wanted to find a point estimate of all blue M&Ms in the bag, I counted how many blue M&Ms there were in the bag, and I had 54 M&Ms total in my bag. And out of all 54 M&Ms, I counted 15 of them were blue. So if I put this into my calculator, that comes out to an almost 28% of blue M&Ms inside my bag. Now, of course, everybody's bag of blue M&Ms is going to have a different p-hat, right? So your bag of M&Ms that you picked and you selected back from your Chapter 8, you might have a different p-hat. I would expect you to, right? Everybody's color distribution in their individual bags is very random. So let's verify that the requirements have been met so we can construct a confidence interval. The two requirements that you absolutely have to meet is you have to prove that it's normal. So in order, again, to prove that it's normal, we have to prove that n times p times 1 minus p is indeed greater than or equal to 10. So let's see. I have 54 M&Ms in my bag. P-hat is 0.27 repeating times 1 minus p-hat, and that is definitely greater than or equal to 10. So I've satisfied that first requirement. Then we have to decide, is my sample independent from each other? So is my sample less than 5% of my total population? Or in other words, my sample that has 54 M&Ms, is that less than 5% of all M&Ms? And of course, yes, there's many, many more M&Ms than what I have in my bag. Okay, so we've proven that the samples are independent, and we've also proved that it's a normal distribution. So let's now construct a 95% confidence interval. Remember, let's write down the formula for confidence intervals. You need a point estimate, and then we need a margin of error. The margin of error is found by this piece of the equation here. So when I plug this information in, I have my p hat, which was 28% blue M&Ms. Then we're going to add and subtract all of this, everything in this yellow area. Again, this is all called my margin of error. So now I have to find my margin of error. My margin of error is going to be calculated by finding my Z, my critical Z, when I'm 95% confident. Eventually, you'll probably start memorizing these because you'll use them so often. But when you're 95% confident, your critical Z score is going to be 1.96. Times p hat under the radical, so that's going to be 0.27 times 1 minus p hat all over n. Now I'm going to put all of that in my calculator, and I'm going to get 0.27 is my point estimate, plus or minus my margin of error, which is 0.1195. And again, remember, this is my margin of error. All right, so if I put this in interval notation, my lower bound will be 0.158 and my upper bound will be 0.397. You'll notice that this range is quite large. 15% to almost 40% is a very large interval. And the reason why that was so large was because my sample size was relatively small. In the previous example, I had a sample size of over 3,000. That's how we were able to narrow this guy down, because we had a lot of people we surveyed. We had a lot of evidence. Well, now we have little evidence. We only have one bag of M&Ms with very few M&Ms in it. So because we don't have much evidence, we have to widen our range to be certain, or 95% certain, that my true population proportion of blue M&Ms is going to be somewhere in this large range. So we would state that we are 95% confident that the true proportion of M&Ms that are blue is between 15.8% to 39.7%. Okay? Does this fall in line with what Mars claims the blue M&Ms will be, right? Mars, the company Mars, claims that there should be 24% blue in every bag. So the true proportion actually should be 24%. And even though we had 28% blue M&Ms, Mars company claims there should only be 24%. But look, it's in our interval. So our interval did include the actual claim that Mars says 24% should be in there. So that's good. So we're 95% confident we actually captured the true proportion, which should have been 24%. So let's do it again. This time let's do 99% confident. Now let's recall what's going to happen. I want to be more confident. So again, what's going to happen to my range? If you want to become more confident, then your range interval needs to widen out to be more confident that you'll hit somewhere in between those two numbers. So I'd like you to pause the video, redo this equation up here. The only thing you're going to change in this whole equation is your critical Z-score. So this number you will find from table 5, which is associated with a 99% confidence, and redo the whole margin of error and find your confidence level now. Okay, I also did it over here. I found that when I recalculated all of this, I got a larger range, which means my margin of error also increased. So my margin of error increased my interval. It is no longer 15 to 39%. It is now the same sentence, but this time it's going to be from 11.6% to 43.9%. So in a sentence, I would state that we are 95% confident that the true proportion of M&Ms that are blue is between 11.6% all the way up to 43.9%. That is a large range. Okay, so now what I'd like to do is show you how to do all of these in StatCrunch.